ready to learn a lot of acronyms today, yeah? Because we saw already a few. We saw CDM is cold dark matter, right? WDM, warm dark matter. HDM, hot dark matter. SIDM, self-interacting dark matter. Exactly. So partially, we saw partially interacting dark matter and double disk dark matter and so on. These are the less known. In any case, so what we have seen is that WDM and CDM are equally likely. So just a minute. Yeah, here. All right. However, in the standard model, we have only one candidate that fulfills one of the essential conditions, which is neutral or with very, very small coupling to photons. And the standard model, we only have one particle that is neutral, and these are active neutrinos. And active neutrinos are, first of all, hot dark matter. Why we know? Because we know experimentally that the mass, we have upper limits on the mass. We have upper limits actually from CMB observations too. So it is smaller than 1 electron volt, typically the masses. And on the other hand, they have to be in thermal equilibrium before BBN, because mostly electron neutrinos have to be in equilibrium or practically the equilibrium. They can have very small departures from equilibrium. And this is because neutrinos and antineutrinos enter into the beta equilibrium, which is absolutely essential to get Big Bang nucleosynthesis right. And this is one of the major issues why we know that there has to be a radiation bath before 4-5 MeV. And this is to give time to neutrinos to become in thermal equilibrium before they decouple. And I have an exercise. I hope the exercises are now posted. Carla, are they posted? One of the exercises is actually to make an evaluation with material that we are going to see now of when neutrinos, the normal neutrinos decouple, when weak interactions decouple. This happens at a few MeV. This is a very easy back-of-an-envelope useful calculation to know how to do. We can discuss, if you cannot do it, we can discuss that in the discussion tomorrow, right? We have an hour and a half discussion again. Okay, so here. They are a hot dark matter, and besides, the amount of them is very, very small. So they cannot account for the dark matter at all. So this is the point, that there are no cold dark matter or warm dark matter particles candidates in the standard model. Some people say, well, sterile primordial black holes do not require new physics. That's absolutely not true. You have to have other scalar fields, other ways of producing. Also, inflation. Inflation, it requires a mechanism, model that is beyond the standard model. You can try to make inflation with the Higgs field. It's very difficult. It doesn't really work, in spite of many attempts. So here it is. So there are no cold dark matter or warm dark matter particle candidates in the standard model. But there are many, many in extensions of the standard model. And here there are a few of them. For example, sterile neutrinos have a spectrum that is almost thermal. And we have seen that actually thermal particles, the limit to be warm, acceptable warm, is about 3 keVs. If particles are in thermal equilibrium or close to thermal equilibrium, then their average energy is related to the temperature. It's about 3 times the temperature. So at 1 keV, they must be in equilibrium. The mass must be at 1 keV temperature. Then their mass must be 3 keV. So 3 keV, around 3 keV or few keV sterile neutrino would be a good warm dark matter. But there are others, gravitinos, non-thermal WIMPs, many more. And cold dark matter, of course, we have WIMPs, axions, and so on, several that we are going to see. Yes? And you tell me, I repeat.
Cold dark matter. It depends of the mass?
It depends on the model and the production.
Okay.
Production mechanism, mostly. Being warm or cold is not a statement about the mass. It's a statement about being cold, non-relativistic, when the temperature of the universe is 1 keV. Warm, becoming non-relativistic, when the temperature of the universe is 1 keV. It could be a particle that is extremely light, axions, for example, but they're extremely cold. They are still non-relativistic at that moment. You can have a particle that is very massive, but produced with an enormous amount of energy, is relativistic, then it becomes non-relativistic at 1 keV. So it is not, and then it would be a candidate for warm dark matter. So it is not mass, it's the fact that they are non-relativistic or becoming non-relativistic when the temperature of the universe is 1 keV, right? So particle dark matter requires physics, new physics beyond the standard model. And the essential point is which. And here there is a little bit of history for the models. So we have an idea of the type of models and how they change with the time in which they were produced. As I mentioned, particle physicists became aware of the fact that there was a problem called dark matter in the late 1970s, beginning of 1980s. Until then, all the models for beyond the standard model physics were models trying to solve problems of the standard model itself, like the hierarchy between scales, between granular unification and the Higgs, the electroweak scale that is solved among columns with supersymmetric and bi-supersymmetric models, or the strong CP problem for axions, and so on and so forth. And then they said, oh, wow, well, these models, if they are viable, they should produce also a dark matter candidate. It was an afterthought. People haven't thought of that before. Then in the 1990s, having dark matter candidates became mandatory. Hey, better in the model that you produce, better you have a very good dark matter candidate, otherwise your model is invalid, right? So it changed. In the 2000s, there was a complete split. And there were many models that were absolutely not made with having any property of the standard model in mind, not to solve any problem of the standard model. But there were, so many searches were going on already in the 2000s and beyond that. And there were many hints. Whenever you have many experiments, you will have always some hints here, there, that afterwards they disappear. And then, in order to explain them, you can produce models that are completely viable, but completely separated from solving any problem in the standard model. And there you have a plethora of different models, for example, all type of models and type of interactions, to dark sectors, as I have mentioned, that come naturally in many of these models, seen through portals. So the idea that in reality, we haven't seen the dark matter in experiments, not because the dark matter is very heavy, that was the WIMP type of thing. It still is possible, but it may be very light, but interacts very, very little with the particles of the standard model, and interacts through very small couplings that are called portals, and then you have a very small coupling. I mentioned one, kinetic mixing with the photons, so the photon portal. It could be a very small coupling to neutrinos. You will have in non-standard interactions for neutrinos, or it could be with the Higgs, etc. Very small portals, couplings. So here you have some of the members of this particle zoo. So WIMPs are the ones that you probably have known the most for forever, weakly interacting massive particles. So they were some of the first because they appear in some of the complete models that were made in the 80s to solve problems related to the standard model, like, for example, this supersymmetric models, composite models like the little Higgs, in which the Higgs is a composite field, inert doublet models, etc. And how they produce those. These are ultraviolet complete, most of them, models. And the way in which you have a dark matter particle is because there is a conserved quantum number. In the case of supersymmetry, you have the LSP, the lightest supersymmetric particles that carry R parity, like the Neutrino, etc. These are the lightest, or the lightest Techni baryon, the LKP, the lightest Kaluza-Klein particle, LZP, and so on. The lightest particle that carries a conserved quantum number within these models. So their production, they reach thermal equilibrium via two dark matter particles annihilating and going back and forth to two standard model particles, other particles, interactions of the type 222, and then freeze out. Or in the decay of another WIMP, this is called the super WIMP scenario, and typical masses are from GeV to hundreds of TeVs. FIMPs, feebly interacting massive particles, or also frozen in massive particles, have interactions of an order much smaller, much smaller than weak. This is what actually characterizes them. These models are not very illuminating. In any case, the models are more complicated, moduli or modulinos in string theory, Gatt scale suppressed interactions, or the famous kinetic mixing, coupled only through kinetic mixing, etc. They never reach thermal equilibrium. And so they are frozen in, freeze in. So freeze in is the opposite freeze out. Freeze out, you're in equilibrium, and then at some point you come out and the number density per co-moving volume becomes constant. Freeze in is instead you produce a little bit, you produce a little bit, you produce a little bit. At some point the production mechanism ceases to be effective, and what you produce, what you didn't, and that is the frozen in. This is a relatively new name for an old mechanism, because this is what happens for the sterile neutrinos, and that was known forever. But this is a new name for a very old process, type of process. The typical masses are from sub-electron volts to 100 TeV, so FIMPs. Then there are SIMPs. This is how I call what Nicolas called these cannibals. I call them SIMPs, strongly interactive massive particles. This is a variation. Many of these ideas started in the 80s, and then they were reprocessed in different ways. In particular, just a minute. Strongly interacting massive particles were actually strongly interacting initially in the 1980s, and they were actually proven not to be there. You cannot have them with strong interactions. But they could be strongly self-interacting, although very feebly interacting with a standard model. So they can be what is called FIPS. In any case, let me concentrate in SIMPs. By the way, maybe you're not young enough. Teaching SIMPs to my undergraduate students in Los Angeles, and they started laughing. And I said, strongly interacting massive particles never made anybody laugh. What's going on? So after pressuring a few people, I realized that there is a new word that has appeared in the internet, simping, which doesn't seem to be so nice for what they told me. And so they were laughing about it. But actually, these names started in the 1980s, actually. Yes, go ahead.
Would all of these models have a constant amount of dark matter throughout, like, as the universe progresses? Like, because I know the WIMPs we say that we wouldn't have like new particles forming, like the rate of dark matter in the universe is the same.
See, with all of this, you can get the dark matter abundance. Yes. These are all made in such a way that one way or the other, you get the right dark matter, the abundance to be the bulk of the dark matter. Yes.
Thank you.
Nicholas actually mentioned one of these, the ways in which you can produce. They reach thermal equilibrium, but in the dark sector. Through these processes, 3 to 2 or 4 to 2, dark matter to dark matter. And of course, when 3 or 4 dark matter go to 2 dark matter, you produce dark matter very energetic. And so in order not to end up with all hot dark matter, because in the end you will dump all this mass into kinetic energy of the particles, you have to have some interactions that actually share this energy with the standard model. So you have to have some standard model particles, you have to cool them down. And in particular, one particular type of SIMP is this elders that was mentioned also by Nicolas, elastically decoupling relic, in which, as he mentioned, actually this is type of SIMP in which the dark matter elastic scattering is extremely important for the decoupling and for the final abundance of the particles. I'm not going to give many details on most of this. It's just an introduction to the type of models. But fortunately, Nicolas talked about this. So actually, this is good. So typical masses can be a very large range, 100 keVs to these are what we are calling now light dark matter. They were part of WIMPs before, but this would be essentially light dark matter is different from WIMPs now, in the sense that WIMPs would deposit enough energy in nuclei to be measured in direct detection experiments, and instead light dark matter would be detected through interactions with electrons. This is the difference, right? But they are lighter. PIMPs, Planckian interacting massive particles. This type of model assumes new physics comes at the Planck scale, and therefore most of these particles have the Planck mass. They are produced in a hidden sector with a gravitational order standard model interaction. The production is soon after a very high reheating temperature inflationary period during the reheating, and there are many variations of this, for example, GIMPs, gravitational interacting massive particles in Kaluza-Klein models, etc. Axions and ALPS are pseudo-Goldstone bosons. Axions were, yes, sorry.
Sorry. It's kind of strange to me to propose a new physics at Planck scale, because in the end, it kind of doesn't matter, because
it is absolutely easy. It's very hidden Planck scale.
Yeah, I worked.
So yes, and the issue is to get the right abundance.
Yeah, I mean, I worked with composite Higgs models. I could say that the composite scale at Planck scale.
It will be very difficult. Yeah, this is the type of dark matter that you would never find.
Yeah, I mean, so.
Yes, so it is enormous. It's frighteningly easy to come up with models of dark matter in which you will never see any other thing but gravitational interactions.
Yeah, it's good.
Frighteningly easy.
It's good to know
so if nature has been kind with us, we are going to find dark matter in any other way.
Okay, I hope so.
It's, yeah, it is. Yeah, it will be very difficult to detect these things. Right? It's true, but possible. In any case, if you don't look, you don't find, right? So you have to look. All right. So axions and ALPS, I will talk more about this. It started with the axions. Axion is the name of the detergent. And I think it's, in the United States, it's not commercialized anymore. In Argentina, it exists as Palmolive. Palmolive is here too, axions. You can say it's a detergent. Frank Wilczek put that name because it cleaned up two problems at the same time. in any case, that was a joke, but there are many jokes in particle physics, you know, the names, in any case, axions. And Alps, another joke, because everybody knows these very high mountains in Europe, they are called axion-like particles, and they share some of the properties of the axion. The axions have to be coupled to gluons. This is the main function of axions, because actually you want to solve a problem in QCD, and instead Alps may not. But otherwise, it's a pseudo-Goldstone boson, and it shares some of the properties. The production can be as a boson condensate or radiated from axion topological defects, and I hope to talk about this in my last lecture, and the fifth one. So, WISPs. This is a very German name, because slim particles is a very strange way of calling slim. You know, slim is like, I don't know how to say, thin in terms of weight. So slim particles. They coined this name in order to indicate either axions, Alps, which have a spin 0, or dark hidden photons. Instead of having to say always Alps or hidden photons, then you can say a WISP, because a WISP is both. It's a boson, can be spin 0, spin 1. FIPS, feebly interacting particles. FIPS are one of the main targets of research at the LHC at this point, and in accelerator physics. FIPS is feebly interacting particle. Feebly interacting with what? With the standard model particles. These are particles with portals, very small interactions and so on. But they can be SIMPs, strongly interacting, and SIMPs are part of FIPS. So there have been, for example, a very large workshop at CERN a couple of years ago, and I think there will be one soon, about FIPS and how to search for FIPS. So FIPS is a very important name to remember, because it is used a lot in accelerator physics. And still there are many others, and these are a few. Dynamical dark matter is a dark sector with a vast number of particle species whose standard model decay width are balanced against their cosmological abundance in such a way that the composition changes all the time, but the density is always the one that you need. The short-lived ones have smaller densities and so on. It's a complicated type of dark matter. Mirror dark matter is equally complicated. Mirror dark matter is a hidden dark copy of the standard model, including everything. The 3 generations, everything dark. That's an extreme dark sector, a dark sector that completely replicates the standard model sector. Q-balls. Q-balls are non-topological solitons created as a fragmentation of scalar condensates, sterile neutrinos, or how they are called now, dark fermions, new names for old particles, dark fermions. Dark fermions could be much heavier than usually we assign to sterile neutrinos. So dark fermions can have any mass. That's a major difference. But otherwise, I would say the sterile neutrinos and dark fermions are the same thing, and they are included in FIPS. So now, this is what we know about dark matter, and we finished. These are all the properties that we have gone through. These are the 8 properties. These define the dark matter. Doesn't need to be a particle, doesn't need to be. So if you find anything else that actually fulfills all these conditions, you have found a new candidate for dark matter. So this particle dark matter requires beyond standard model physics, but you have to take care, as she asked, that actually you can reproduce the dark matter abundance. And the issue is that, so any particle, any dark matter candidate is required to have the dark matter density, to reproduce the dark matter density, because that is something that we measure. The caveat is that the computation of the relic abundance and velocity distribution of particle dark matter candidates produced before 5 MeV depends on both of them, depend on assumptions made regarding the thermal history of the universe, and therefore it can be different depending on your assumptions. There are usual assumptions that are made. The universe is radiation dominated and having the standard model degrees of freedom, etc. But those are assumptions. You have to be very careful without confusing what is an assumption and what is not. Okay, so I will mention a few things. So this is a parenthesis because I have seen that many people here don't know much of cosmology, and therefore this is a minor parenthesis for something that I will use, which is the relation between the Hubble expansion and the lifetime of the universe.
Are you going to stay here for general questions?
I mentioned what?
Are you going to stay here for general questions in the afternoon?
Yes, today I'm staying.
I ask you then. Okay.
Oh, okay.
It's a general question. So.
It's a general question. Thank you, because then we advance and then we discuss this in the discussion. Yes. It was only yesterday that I was finishing my part 2, which we are going to start today, because otherwise there was no part 2. So, idea. Okay, so no, today I'm going to stay. So here it is, a very minor introduction to what is the relation between H and the lifetime of the universe. So, as you know, the Hubble expansion was discovered by Edwin Hubble, and that's why it carries its name, Hubble expansion. And it is this property that actually the velocity of recession of faraway objects that are not gravitationally bound to us is equal to a constant times t. It's a constant nearby, but actually it is, all of these are time dependent. So Hubble measured this parameter to be very small, which created a problem. But in any case, H is about 70 kilometers per megaparsec per second. Many times you have little h. So you have 100 kilometers per megaparsec per second times little h. H is a reduced Hubble constant, and h is about 0.7. It's about 0.7. There is a problem now, as you know. There is a problem with the Hubble, the measurement of the Hubble constant, because nearby universe measurements of the Hubble constant and early universe measurements of the Hubble constant at present, which is used as a parameter to anchor parameters in the early universe, give different results, slightly different results around 0.69 or 0.73, but outside the range of, they are more than 3 sigma apart now. They are 4 sigma or close to 5 sigma apart. So this is the H naught problem right now, the open problem. But for us, it's 0.7. Please ask if you have any problem here. So, as you know, the expansion has no center, or interdistances grow in the same way. You can see it in this way, okay? So this is the scale factor. This is the definition of a scale factor. A current distance in the past would change according to this factor. So if I take the time derivative, you see that d dot would be the velocity of recession. This is d dot. And then I replace, this would be a dot, and then I replace d0 by d0 in the equation, and I get this. So H, the definition of H is a dot over a. So this is the definition of the Hubble constant. Actually, it's not a constant, it's a definition of the Hubble parameter. The Hubble constant is the value of the Hubble parameter at present. Sub-zero in cosmology usually indicates now. So T naught, T sub-zero is the value now. H naught, H sub-zero is the value of the Hubble constant now. Okay? So now, so the expansion of the universe has no center. And if you want to understand this, this is something that I do with my undergraduate students. You have this series of dots here. You take a photocopy machine, you can put it in a slide. you take a photocopying machine, you amplify that by 20%. So it's the universe in some time in the past. These are the same things now, a little expanded. And then you put one of these dots immobile, because this is your point of observation. You're not moving with respect to yourself. And then you see that actually all the other points seem to be radiating from you, and the dots that are more distant from where you are, your point of observation, actually are more separated, namely they move faster. So all this expansion that is proportional to the distance is just an illusion of our point of view for interdistances that are growing. So we are always the center of expansion, but another observer that would be in a different point would see exactly the same thing. So this is, okay, sorry. Now, the other thing is that the lifetime of the universe is approximately h⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ it will be exactly h to the minus 1. This is the scale factor, and this is time. And we say that we start time, t equals 0, at the moment a is equal to 0. This is the definition. In a universe that is radiation-dominated, this changes by a factor of a half. It's 1/2 of h to the minus 1, the lifetime of the universe. In a universe that is matter-dominated, it's 2/3. But I will take it to be h to the minus 1. So the inverse of the expansion rate is the lifetime of the universe, right? This is what I'm going to use. Okay? Some of you are inscrutable. I do not know if this is understood or not. Is this understood? Okay, right. So now we can define what is chemical equilibrium and what is the coupling. So here it is. Chemical equilibrium is when the particle number changing reaction rate is fast enough. Nicolas used it already. And kinetic equilibrium is when the momentum exchange reaction rates are fast enough. Fast enough with respect to what? Whenever you say fast or slow, or you say big or small, you have to say with respect to what? With respect to what? With respect to the rate of change of temperature. Because you are trying to keep up equilibrium in a medium whose temperature is changing. So you have to adjust to a changing temperature. And so your reaction rate has to be larger than the reaction rate at which the temperature changes. Since in an adiabatic expansion, the temperature is inversely proportional to the scale factor, T is 1/a, T dot over T is minus A dot over A. So the rate of change of the temperature is the same as the rate of change of the scale factor, which is the Hubble parameter, right? The inverse of the reaction rate is the reaction time. So when I say that the reaction rate has to be larger than the expansion rate, I'm saying that the reaction time, which is the inverse of this reaction rate, has to be smaller than the lifetime of the universe. And you can think of it, if the reaction rate would be larger than the lifetime of the universe, that means that there were no interactions, right? There are no interactions. It means that the particles interact with a characteristic time that is much longer than the lifetime of the universe. Particles don't interact. So in order to have reactions within the lifetime of the universe, you have to require that the reaction rate, that the reaction time is much smaller than the lifetime of the universe. The reaction rate is much larger than the expansion rate of the universe. Okay? So when that happens, this is relativistic kinematics and so on, you will have this for the particles, this is the number density. So one can compute the number density, and this goes as T cubed. And for relativistic particles, then you will have this characteristic Boltzmann suppression, e to the minus m over t. Okay? Now, gamma of t usually decreases faster with temperature than h. So that means that particles can be in equilibrium, and then they become out of equilibrium. So the moment in which they become out of equilibrium, we call that decoupling. Huh? So chemical decoupling or freeze out is when the number density is fixed. Namely, you don't change any longer the number of particles per co-moving volume. Kinetic decoupling is when the exchange of momentum with the radiation bath ceases to be effective. In both cases, the different reaction rates, these are different reaction rates, were faster, were larger than h before, and become smaller than h after. Okay, this is decoupling. Okay, obviously we need to know what h is, and for that we need this equation, Friedmann equation. I mentioned that there are two equations that come, two independent equations that come out of Einstein's equations for the universe, for an homogeneous and isotropic, spatially homogeneous and isotropic space-time, and this is the equation. K is 0 for our universe. We have measured. This is the curvature term, is 0. Lambda is irrelevant in the early universe. So in the early universe, h is proportional to, h squared is proportional to g. This is g is the gravitational constant, which by definition of the Planck scale is 1 over the mass, the Planck mass square. And rho is, in the equations I will use, is radiation dominated. And the radiation dominated rho goes as t to the 4th, and therefore h will be essentially t squared over m Planck. And that's what I will use. T squared over m Planck. It will be a square root of g rho. Okay, square root of g rho. So this is what I will use whenever I need some estimate for the scale factor for h. Okay, now we go to this decoupling of the thermal WIMPs, and here I'm going to write something. Okay. So I didn't think of talking about the Boltzmann transport equation, but Nicolas mentioned it, and then I want to make contact with what I use usually to indicate chemical decoupling, which is when the annihilation rate becomes smaller than h. And you have an exercise precisely to prove what I will just write on the blackboard. So here it is this equation. So for example, you have dark matter particles going to, call it F bar, could be any particles of the standard model. These are standard model particles, and this is my dark matter particles. So then you have dn of chi dt. This is the equation plus 3h and chi is equal to minus sigma a v, and then n chi square minus n chi equilibrium square. And these terms can be easily seen. So assume that there are no annihilations, there are no interactions. So this term accounts simply with the expansion, for the expansion. In the expansion, n, of course, what is n? A number of particles divided by the volume. So this goes as 1 over a cube. If there are no production or destruction, this is n will only change because the volume changes. And so when I take the derivative, this will be just minus 3 A dot over A n minus 3 H n. And this is the equation that I will get, the n at the x equal minus 3 nh that I pass here. So this is just the expansion. Now, assume that I will have only annihilation, no expansion, no creation, only annihilation. So if I have only annihilation, so this term with this one, this accounts for annihilation. And the annihilation would be the following. If you have just annihilation, n becomes proportional to e to the minus t over the typical annihilation time. This would be what you have. And then that means dn chi dt is minus n over ta, and ta is 1 over the rate of annihilation, and the rate of annihilation is n sigma a v. This is the rate. That's it. So this accounts for annihilation. So now this term, so this accounts for chi bar going to f bar. This one accounts for f bar creation. And here you can do a Gedanke experiment. Stop the expansion. I can do it. It's just stop the expansion at the temperature T. Wait long enough until you get equilibrium. When you get equilibrium, so wait to get equilibrium at temperature T. And that means that dn chi dt in equilibrium should not change, right? It's equilibrium, no expansion, nothing, right? Just equilibrium. So this should be 0. And if it is 0, and you're in equilibrium, this will be the equilibrium, and therefore you need this minus to get into account, right? You need precisely this minus in order to get 0. In order to get this 0. So this is it. This is the. So if you have never seen this equation, now you understand the terms. Not how to derive it. You have to go to a book, for example, Coleman-Turner book or whatever. But what I would like to say is the following. As Nicolas mentioned, instead of having n, the number density, we like to use y. Y is n over the entropy S. So here you have that this is proportional. N is just a number divided by a cube. And S is proportional, it's a number fixed, proportional to T cube, dominated by radiation, right? It's T cube. But we know that due to the adiabatic expansion, T is inversely proportional to 1 over 2. So this is a constant multiplied by n. So when y becomes constant, the number density becomes constant. The number per comoving volume, which is the number that I'm assuming there. Remember what is a comoving volume. A comoving volume is what corresponds to a fixed volume now. So take a 1 cubic volume, 1 meter cubic volume. In the past, this would be multiplied by a cube. So it will be a cube times 1 meter cube. So this is the comoving volume. Okay, and then we use also x, which is m over t. M is the mass of this dark matter particle. Okay, with this, using the equation for entropy, then you can put this. You can rewrite the same equation in equation dy dx. And you can see that you can put this minus the annihilation rate, which is this. Here, this is 1 over the annihilation rate the annihilation rate over h, y square over y equilibrium square minus 1. And what is gamma? A. This is n equilibrium sigma annihilation, so chi in my notation, chi car bar going to f bar, the annihilation multiplied by v. And this indicates integrated over the distribution of the particles, the initial particles summed over the final. So this is a thermal averaging, okay? So now you can see the condition that I usually, the simplified condition that I usually use, which is this one. When gamma over h becomes much smaller than 1, then dy at dx becomes constant, y becomes constant, okay? The number n per comoving volume is fixed, okay? So this is the way in which one can make contact between Boltzmann equation and this simplified condition. Gamma over h is what enters there. Okay. So here we have that gamma over h. So can we switch off the, because otherwise you cannot. Yes. Shout. The comoving volume is a volume in which you do not take into account the expansion of the universe, which is trivial. So it would be fixed, except for the, so it accounts to the actual production or destruction of particles. Because even if you have a fixed number of particles, the number density always changes in an expanding universe, because it's always decreasing, because the volume is changing. So you say, no, let me consider a fixed volume. So essentially, if you take A, the value of the scale factor equal to 1 now, then the comoving volume is always equal to the volume now. So it will always be 1 meter cube in my example. Right. If you imagine I cannot, in 4 dimensions, I cannot do it. But if you imagine that our universe is a 2-dimensional analog of expanding balloon. Okay, so here you have a small balloon, a big balloon. You have comoving coordinates are coordinates that are fixed to the balloon. So this here and this here represents exactly the same comoving, in this case, area. In the case of 3 dimensions, it will be volume, right? Okay, all right. So now we can move ahead. And yes, oh, I forgot to bring yes, I put it for 3 minutes. Thank you. Okay, so so here it is. So so we assume that WIMPs reach thermal equilibrium early on. So we start at the temperature that is for sure larger than the freeze-out temperature, or freeze-out is the same as decoupling. It's the same as chemical decoupling. So chemical decoupling, freeze-out happens, and I show you when the annihilation rate becomes smaller than the expansion rate, right? And we assume that afterwards there is no entropy change. So now here it is. This here is y. Now I can tell you what this here is y. It's essentially y. At this point, with n equal 1, any x, you see that x equal 1 corresponds to the moment in which particles are becoming non-relativistic. So here the particles are becoming non-relativistic. The mass is larger than the temperature. And so here you have this here, the equilibrium is regulated by the Boltzmann factor, e to the minus m over t. It's an exponential decrease. So these particles decrease while they meet each other to annihilate. And then you can use this picture picture that is almost correct, depends on what is your frame, in which a cross-section is actually the area that interacting particles present to each other. So big cross-section means big areas. So if you have big areas, right, even if you have fewer particles, you still keep meeting, right? If you have very small areas, then you need a lot of particles, because otherwise you don't meet. So here it is that actually larger cross-sections means that you remain in equilibrium even when there are fewer particles. And so, you know, people say, in order to remember, the weak prevail, like in the Bible. In this case, it might be true. In the Bible, I'm not sure. But here means the weaker interactions actually have larger remaining density in the end. Huh? And so here it is that for weak interactions, the coupling happens when m over t is about 20. For strong interactions would happen about 40. Okay, so, and this is the point at which it happens, this miracle. I put this here 10 to the minus 26 centimeter cubed per second, because this is the way in which astronomers like it. But particle physics like natural units. In natural units, this is 10 to the minus 9 inverse GV square. 10 to the minus 9 inverse GV square. Huh? So if you put here a typical cross-section, which is a weak cross-section, you know that the weak cross-section will be given, and this is a way, I mean, I'm not sure if you know how to estimate cross-section. Here you have q square minus m square. This is the propagator, and this is G weak. And then sigma would be proportional to this. In this case, if m is much larger, this is what I'm assuming, then you will have this amplitude. So this is an amplitude square times a factor that only takes care, a factor that depends on the initial energy in the initial state, that takes care to get the right dimensions. And then you get that this is GW square over m square. And you can have, if they are WIMPs, you can have here the mass square, something like that. This would be to the fourth, sorry. So this is approximately what we call G Fermi square, the mass square. G Fermi is 10 to the minus 5 over GV square. So here you have 10 to the minus 10 over GeV to the fourth. And then you have here the mass square. So if you have something like that, you immediately know what the mass needs to be in order to get what you need, which I said is 10 to the minus 9, 1 over GeV square. You need particles that are of order GeV. This is the WIMP miracle. In reality, it's much less of a miracle, because in any particular model that you have, this is an important constraint, and you have to make sure that actually it works this way. Okay. Doing things a little bit better, you get this equation, actually, for omega. And because you see that annihilations can happen in S wave or in P wave. You know what is S wave annihilation and P wave annihilation? So when you have annihilating particles, here you have 3 minutes. I'm always overestimating what I can fit in a lecture. But in any case, I made a long parenthesis. So when particles are annihilating, they can be back-to-back impact parameter 0. This is L equals 0 annihilation is S wave. But you can have also something that goes like this and then annihilate, and this is L not 0. And L, as you increase L, you have S wave, P wave, D wave, and so on and so forth. Okay, there are some particles that can only annihilate because of essentially kinematics, For example, Majorana fermions cannot annihilate in S waves. It's a particle requirement because they are identical particles and they must be, the wave function has to be odd among exchange and so on. You can have only B wave annihilation, and of course then the equation changes. And this is an important distinction for limits that come from indirect detection that apply to S wave annihilation but not to P wave annihilation. In any case, let me mention this and then we are going to finish. Kinetic decoupling is when the reactions that exchange momentum with the radiation bath cease to be effective. Now, this depends on the scatterings, not annihilation, but the scatterings. And even when there are very few dark matter particles, there are many, many standard model particles. So the scattering keeps on going for a very long time, even when annihilation ceases. So and moreover, it's not only the scattering, but it's the exchange of momentum. And the exchange of momentum becomes very ineffective when you have a light particle colliding, small ball, big ball, right? Just in collisions. The momentum of the big ball, massive particle, is changed very little. So there is actually a factor here, T over M. In any case, when you have to take all of this into account, and then you see that the kinetic decoupling happens much later. At that point, the kinetic decoupling, that means that the thermal velocity, the velocity of the particles, is not the thermal velocity, which is essentially the temperature over the mass, square root of the temperature over the mass, and it starts instead redshifting. Redshifting. The redshift of particles, you can see that the redshift of non-relativistic particles, the velocity changes as 1 over the scale factor. And you can see that if you see that P, there is a de Broglie wavelength, P goes as 1 over the de Broglie wavelength. All wavelengths, including the de Broglie wavelength of a particle, change with A. P is mv. V, it changes as 1 over A. Okay, so the story is the following. At the moment they decouple, the WIMPs are very hot, are almost relativistic, 0.3 of the velocity of light. Then they keep on decreasing while they are in equilibrium. Their velocity keeps decreasing, is a square root of the temperature over the mass. They are still in thermal equilibrium. Yeah? And then they decouple, they become extremely cold. Imagine, for example, what is this factor if you have a decoupling that happens at a GV and you are at the temperature that is a KV. Here is KV over GV, it's an enormous factor. So they are extremely cold. The velocity is very, very small. So if you have a velocity-dependent cross-section, you can imagine how much it changes with the velocity. The velocity is very, very small, until WIMPs fall into structures, and then they get the virial velocity, and the virial velocity in a galaxy like ours is like the velocity of the sun. You have a problem on virial velocity, estimating virial velocities. I advise you to go through because it is very illuminating to compute the virial velocity of different structures. In any case, it's about 10 to the minus 3 C. So they heat up. And this is very important if you have bounds on the annihilation cross-sections at different ages. You have to say, oh, well, if the cross-section is independent of velocity is one thing, but if it is dependent on velocity, it can be extremely different when I'm measuring things and when I'm at the decoupling, right? So this is what we are going to see next. I think we are going to finish here. We'll start with caveats to this story next time.
Further questions?
Coffee.
Has everybody signed this sheet? So please, before you leave, those